Greetings, fellow mathematicians. We're going to turn our attention to solving second-order ODEs now with non-constant coefficients. These turn out to be a lot harder to solve. Some of you might be getting to them soon in your upper-level science and engineering courses, where you'll start to encounter all sorts of special functions. Now, in my differential equations course, I like to start this topic with a very special type of second-order ODE with non-constant coefficients, with what's called a Cauchy-Euler equation. Now first, the general form of a second-order ODE with non-constant coefficients looks like this. We have y, its first derivative and second derivative terms, but instead of numbers or constants multiplying them, we now have functions, a sub 0, a sub 1, and a sub 2, all of which are functions of x. Now, depending on the functions, that could make it very difficult or impossible to solve exactly for what the solution y is. A Cauchy-Euler equation, there's very particular forms for these functions, and they're very simple. We're going to start with powers of x, where the power of x matches the order of the derivative. So here we might have an x squared term, here we might have just an x term, and here just a constant term. So let's write down the general form of a Cauchy-Euler equation. It looks something like ax squared times y double prime. Notice the power is going to match the order of the derivative. Now for a1 of x, we're going to have just x to the first power. That might look like bx times y prime. And then we have a constant times y. All right, and that is what's known as a Cauchy-Euler equation. You might also find it described as an equidimensional equation. All right, now the way we solve this is very similar to how we started solving a second-order ODE with constant coefficients. So let's go ahead and get rid of the x squared and the x, and we're going to go back earlier to when we saw an equation of this form, ay double prime plus by prime plus cy equals 0. All right, we know how to solve that. We started by assuming we had exponential functions that were solutions of the form y equals e to the rx, and that led to us getting the characteristic equation. Now, we did point out in a previous video why we might expect exponential functions to be solutions, and we're going to take a similar starting place here with a Cauchy-Euler equation, and I think it's actually a little bit simpler than assuming exponential functions as our first choice for solutions. Take a look at your differential equation and think of a function for y, or type of function, such that when you add that function and a bunch of its derivatives, which might be multiplied by powers of x, you can get it to come out to equal 0. Well, if we have powers of x in there, we might try y as a power of x. So we're going to try y equals x to the m, where m is the power. And we're going to determine, basically by plugging this back in, what the values of m are that make this a solution. Now, we're going to kind of parallel the work here, just so you can see the similarities. If you can get the characteristic equation over here, you can get the similar equation over here, but not for r, but rather the power of x, an equation for m. So we're going to need to calculate the derivatives of this function. So let's go ahead and do that. We don't need anything fancy, just the basic power rule going all the way back to Calc 1. So bring your power down and then subtract 1. And we're going to need a second derivative. So let's go ahead and differentiate that again. Be careful, bring your power down, m minus 1. And then again, we subtract 1 from the power. So let's go ahead and parallel that with the work over here for when we have a second order ODE with constant coefficients. We start with our assumption for the solution, y equals e to the rx. Calculate your derivatives, r e to the rx. And then for the second derivative, r squared e to the rx. Here we use the chain rule. Here we use the basic power rule. Now, the reason we were able to get the characteristic equation is, notice all three of these terms contained e to the rx, which allowed us to factor it out. Well, notice the problem here, due to how the power rule works, the powers aren't the same all the way through here. They all got reduced by 1. But what makes Cauchy-Euler equations very simple to solve is, notice you have these terms multiplied by matching powers of x. So let's go ahead and take these. And your first derivative term, we're multiplying that by x. Now what would happen here if I multiply this by x? Multiply the right side by x, or x to the 1. When you multiply x's, you can add their exponents. Add m minus 1 plus 1 for x to the 1, you'll get m. So your x y prime term, that comes out m, that's the power that you brought down from applying the power rule the first time, multiplying by x, adds 1 to that exponent, canceling out the minus 1, giving you back x to the m. And notice your second derivative term, that gets multiplied by x squared. Again, multiply this by x squared, you have x to the m minus 2, multiply by x squared, you can add 2, and you'll get x to the m. But you have extra factors. So your x squared, y double prime term, multiply by x squared, that bumps back up to x to the m, but now you have extra factors. M times m minus 1, x to the m. And at this point, once you've multiplied by those matching powers of x, now this work is very similar here. Here we had e to the rx present in every term. Now we have x to the m. All right, and thinking back to earlier, we know what to do with all this. We plug them into our differential equation, and that converted to what we called the characteristic equation. And we're going to write it down in the general form. We're going to factor e to the rx out, since we already were aware of that. So we get a r squared. We're factoring e to the rx out. We get b r. And then c. There's no extra r term. We're factoring e to the rx out. Only y prime and y double prime give you factors of r. All right, and what we have here from your solutions, y equals e to the rx, we now have a simple quadratic equation to solve for r. Now our work here is very similar. Notice if I take these three quantities, these are essentially how you start solving every Cauchy-Euler equation. Notice when I plug these all back in, all three of those terms contain x to the m, so I can factor it out just like I would have factored out e to the rx over here. So if we plug in, this converts to now to something that we're going to call not the characteristic equation, but for a Cauchy-Euler equation, this converts to what's usually called the auxiliary equation. So we're going to plug these in, recognizing that we can factor out x to the m from all three terms. So if we do that, just be careful. We have your second derivative term here multiplied by x squared, but you have that coefficient of a left. So we get a times m minus 1. You have your xy prime term. There's a factor of m, but it's getting multiplied by b. So plus bm. And then you have your cy term. We're factoring out x to the m, so we just have c. And even though these are very different types of second-order differential equations, constant coefficients versus non-constant coefficients, notice due to the structure of the differential equation here, it was those powers of x that match the order of the derivative. Both of these differential equations convert to quadratic equations. Here we have a quadratic equation for r, and here we have a quadratic equation for m. We know how to solve this. Let's go ahead and get to the three different types of solutions that we're going to get for m, just like we had three different types of solutions for the roots of the characteristic equation. Now that we know how to find the auxiliary equation, the quadratic equation for m, where m is the power of x in your solutions, we just need to go over the three cases here that you get with any quadratic equation. So expand this, distribute, you'll get a quadratic equation in m. Try to factor it. If it doesn't factor, use the quadratic formula. Now, as before, there were three cases for the characteristic roots. Now we're going to find the same three cases for the auxiliary roots. And just to go over them, we have the case here of distinct real roots, or distinct real values for m, m1 and m2. Each value of m gives you a power of x. All right, that's very simple. Each power of x gives you a solution. We take a linear combination of those to get our complementary solution. Since right now, the right-hand side is 0, these are currently homogeneous ODEs. All right, the next case would be if you have a repeated real root. You do get a power of x, but like the case of a repeated real root here, you can go through the method of reduction of order and how to find a second solution, and you'll see before where the x comes from. Now, if you go through that procedure, you get natural log of x as the extra factor. So if y1 is x to the m, y2 is x to the m times natural log of x. That's the case for a repeated real root. And then the most complicated of all is the case for complex roots for m. Now, just to not confuse the solution over here, previously we denoted the complex characteristic roots in the form a plus or minus bi. I just like to change them from a and b to alpha and beta, so that way my students don't get confused with the two different complex solution cases. So we have a real part alpha, imaginary part beta, and we just plug those in to this solution. It's very similar over here, but these are a lot more peculiar because inside of your sine and cosine terms, you have beta, the imaginary part, times natural log of x. Where does that natural log of x come from? Well, right after this, we're going to take a look, and anytime you have complex powers, and keep in mind here, your value of m, in this case, that would be a complex number up there, you're going to use Euler's formula almost every single time when you encounter imaginary or complex powers. Now, hopefully this wasn't information overload, but I find it's kind of nice to see the similarities between second-order ODEs with constant coefficients and what we're learning about now, a Cauchy Euler equation. There's a lot of parallels, but enough subtle changes. So let's go ahead and get to the first major change, why there's beta natural log of x inside of the sine and cosine terms. And to do that, we're going to use Euler's formula. We're now ready to answer a fundamental question in mathematics, one that you probably never answered before this, which is, how do you understand complex powers? Now, early in your mathematical journey, you learned about integer powers, then negative powers, and then fractions or rational powers, but you never really addressed what a quantity raised to a complex power means, or how you understand that. Well, we're forced into that now when we have the solution x to the m to a Cauchy-Euler equation in the case where m works out to be a complex number. And we're denoting that complex number as the form alpha plus or minus beta I. I'm going to focus for this calculation on the version or solution with a plus between it. You can go through the work here, replacing the plus with a minus, and it's very similar. All right, so our first step is we're going to replace m in that solution with the complex value, alpha plus beta I. And since we're adding in the exponent, I can rewrite this as a multiplication of bases. So in other words, rewrite this as x to the alpha times x to the beta I. Alpha and beta are both real numbers. We think of alpha, that's called the real part, beta, the imaginary part. But they are both real numbers. Now, this part, x to the alpha, x raised to a real number, we understand that. We need to see how we can rewrite or understand this part, x raised to that imaginary power. And anytime you encounter imaginary or complex powers, the key or trick is almost always going to be using Euler's formula. But there's an immediate problem. Here we have base x, but Euler's formula is base e. And I'll confess, I don't remember or ever use the change of base formula for exponentials or logs. Instead, I like to use a sneaky trick or formula that goes all the way back to your pre-calculus course. We're going to use this cancellation property that e raised to the natural log of x equals x. Now, you've likely been using that all over the place. How we're going to use that is we're going to rewrite that base there, x, as e to the natural log of x. So let me go ahead and think of x having a set of parentheses around it, and we're going to go backwards. I'm going to rewrite the base x as e to the natural log of x. We have x to the alpha, and now in parentheses, e to the natural log of x. Outside, you still have the power beta I. And now, fudging some of the details, some math professors probably want you to prove that you can use your property of exponents in the case of imaginary or complex powers, but they work, so let's just use them. You have an outer and inner power, you multiply them. So we'll have the x to the alpha part, and here I'm going to multiply and rewrite the power here as e to the I beta natural log of x. And probably as soon as I write that, e to the I beta natural log of x, it probably clicks and you see where inside of the sine and cosine parts that you get beta natural log of x. Now let's go a little bit further so you can see exactly where those two types of solutions come from in the case of complex values for m. Now we can apply Euler's formula. And we're going to use Euler's formula up here, where we're going to replace theta with beta natural log of x. We're pretty much done. We're just going to carry the x to the alpha factor here. and we apply Euler's formula, we're going to get cosine of beta natural log of x. And then plus I sine of theta, again where theta is beta natural log of x. And we're going to distribute through the brackets or parentheses, and we'll get x to the alpha times cosine of beta natural log of x, and then plus I times x to the alpha sine of beta natural log of x. And that's as far as we're going to take it. What we've done is have converted a complex power of x to a linear combination of this power of x multiplied by a sine or cosine of beta natural log of x. Now, essentially what this shows is a way to convert between these two different descriptions. You could have your two solutions. Here in the case for each complex power, one with the plus, one with the minus, and that is one mathematical description for your solutions here. You have two solutions that are linearly independent, and you can work with that. But generally, in a differential equations course, we don't write our solutions using complex or imaginary values yet. So what we do is convert, and that's pretty much what we've done here. We convert to an equivalent set of linearly independent solutions, which are x to the alpha times sine of beta natural log of x, and the other linearly independent solution, x to the alpha cosine of beta natural log of x. And notice here, your two solutions involve no imaginary or complex numbers. So generally, again, in a differential equations course, this is preferred, but maybe later in higher level mathematics, you'll be comfortable working with these versions. All right, that completes how we find those two solutions in the case of complex values for the auxiliary roots m. And again, m, that was your power of x in the solution to a Cauchy-Euler equation. I hope you learned a lot. If you did, support the channel, like and subscribe.